谁的耳朵？这样，是吧？哦，好，抱歉。我在这。各有在重述。这样，哦。
It's about time to start, and since everybody is ready for the physics fight this morning. I'm Yuan-Shu from National Taiwan Normal University. Of the physics of the TYPT this year. And today is the final physics fight of the TYPT 2022. So I would like to announce the starting of the physics fight this morning. So let's start from introducing all three teams, starting from the reporter.
We are Team Miracle from 建国中学. I am 张雅晴、徐德仲、陈宇俊、杨佑宇、戴志荣。
Hello everyone, we are from Onader from Taipei American School, and I'm Captain Kendall Chan, Alex Dong, Justin Wang, Kenneth Mo, and Xiaoting Lee. Thank you.
Hello, we are Team Excels here from Xiedong Zhongxue. I'm the captain, Zhu Chengkai, and this is our teammates Wu Hanxu, Lin Xiyuan, Hou Bingqian, and Cai Yuqing. Thank you.
Okay, so next I would like all the jurors please use the microphone and introduce yourself.
Morning, everyone. My name is Hong Yixuan from Taiwan Normal University.
My name is Wei from
Good morning. My name is Fang Yuo from Taiwan Normal University.
My name is Zhong Taoren from National Taiwan University.
From National Taiwan Normal University.
I Wei from National Taiwan University.
Good morning everyone, my name is Jiang Zidang from National Taiwan Normal University. Thank you.
Good morning. I'm Hong Zhao from National Taiwan Ocean University.
From National Taiwan Normal University.
Good morning, I'm Zhe Yonghong from Tampere University.
Hey, good morning, everyone. I'm Wen Qinling from National Taiwan Normal University.
Okay, finally, come back to me again. I'm Yuan-Shu. I'm the chairman of this, the physics fight this morning. Usually, a chairman will also give the score, but today I will focus on making the competition go as smooth as possible, so I will not give score. Okay. So this morning we have three teams. All three teams were selected by the selected five starting from March 4 to until yesterday. So all three teams were, after selection, they pick up one problem for presentation. So this morning we will skip the challenging from opponent to the reporter and accept or rejection by the reporter. So we will start directly from the preparation 5 minutes. Okay. So for the first physics fight, the reporter will be Miracle and all-nighter, and the reviewer will be Garcia. The problem to be presented will be number 7, 3-sided dice. And so let's start the clock. Now 5 minutes for preparation. quick notice that this hall, the echo is pretty strong. So anyone using the mic, please all the audience turn your cell phone into the silence mode. Thank you. And if you want to receive any call, please maybe go outside the hall. Otherwise, the sound will be pretty loud. Okay, the preparation time is up, so please start your presentation. 1 minute, please.
Jefferson, I'm the reporter from Miracle and I'm going to report Robert. Please study that. physical and geometrical characteristics of a light, so it has the same probability to land on this side. And one of it is that three key questions. First, what should be the characteristic of a fair suicide index, and does the fair suicide index exist? And final, how the friction affect its probability? It's a demonstration. This is an overview of my presentation. First, here comes some terminology that we will use throughout my presentation. First, the top and bottom slide surface are defined as base, and this part is defined as side, and H is the height of the cylinder, and D is the diameter of the cylinder. And this is a side view of a three-side index. This angle is defined as phi, and the aspect ratio is tangent phi with H over D. And we did a simplified static model that here are two assumptions. First, the result only depends on the contact angle of this and the geometrical property, which is phi, and which means that we didn't consider the rebounding of the cylinder. And next, the contact angle theta between 0 and 180 degrees, and it distributes evenly. So, the position of the center of mass determines the result as it controls the direction of gravity torque. Like in this diagram, it will land fast air up. And this is case 2, and it will land inside. And this is case 2 as well. So now we can know that the probability of landing on its side is P, and it's a function of the height and diameter. And so we can know that the P is equal to this. And so a fair suicide index should obtain the P equals to 1/3. And in this case, the phi is equal to 30 degrees, and the aspect ratio H over D is equal to 1 over the square root of 3. And so we did an experiment. We toasted each cylinder with spinning like this, and on a flat smooth stone surfaced by my hand, and toast each cylinder 2,000 times to count the probability of landing on its side. And this experiment result. The red line is the theoretical line, and the black dot is our data. And as you can see in this part, in reality, when the ratio is very small, the dice is much less likely to land on its side. And this is simply because the linear velocity and angular velocity, which are ignored in our previous static model, easily make the cylinder fall. And in this part, the theory predicts a lower probability on side. And then we take a closer look, you can see that this part, the fair ratio, which is 1/3, is predicted by a model is larger than our experiment. So there must be an influence of physical conditions. So let's talk about the physical influence. And we introduced the concept of initial conditions. And first, the identical conditions only produce only one certain result. And because if all the initial conditions are controlled very exactly, then there's no probability. So the probability is based on a range of or a distribution of uncertain initial conditions. And here are some terminology. This is the diagram of a moving cylinder, and N is 1 over vector of mass, and V is linear velocity, omega is angular velocity, Y is release height, and there are two extra conditions, air resistance and friction, which are environmental conditions. And here we've got a very intuitive observation that if we toss the cylinder in very high linear velocity, then it seems to have a very high probability to land on its side. And this is the experiment result. this line, the blue line is we toss the cylinder in very high linear velocity that the velocity is larger than 10 meters per second, and the orange line is we just toss it without any linear velocity. And as you can see, it's obvious that the blue line has a very high probability of landing on its side. And this is the reason. So we know that here are the first horizontal linear velocity. This diagram is a 3D diagram that rolling cylinder, and it's moving on this direction, so the friction is fixed and the force is fixed. And we can know that the variation of angular momentum can be described as this. And so we can know that the friction and the force can create a variation of angular momentum. And the new angular momentum makes the cylinder that has a tendency to land on its side. And when the velocity is larger, friction acts for a longer amount of time. So it has a larger variation of angular momentum, and it will persist until it stands up. And here we did a simulation that we simulate with random initial angular velocity and the vector n and release height within a certain range and distribution. And by controlling the linear velocity, we can know that the relationship between the probability of landing on its side and the velocity. And this is the simulation result. The y-axis is the probability of landing on side, and x-axis is the initial linear velocity. And as you can see, when the linear velocity gets larger, the probability gets larger. And here are other initial conditions. If we toss the cylinder without any linear velocity, but because it's spinning, so when you contact the surface, the rotational energy can be converted into kinetic energy, so the linear velocity increases. So now we can know that all the initial conditions can affect the terminal velocity. So we can describe the P of landing, the probability of landing on side as this, a function of linear velocity, angular velocity, release height, vector n, and f. And then f is all the friction during the procedure. And so now we can know that probability is a function instead of a constant, and the distribution of all the initial conditions are centered. And different distribution of initial conditions lead to a different probability. And so a perfect three-sided test does not exist because the initial condition and the distribution of all the initial conditions can be different. And here are experiments that we toss the cylinder in different ways. And the blue dot is we roll the cylinder along my hand, and the orange line is that we toss the cylinder without linear velocity, and we just spin it. And as you can see, rolling the cylinder along my hand has a higher probability of landing on side. And here is the explanation that when rolling the cylinder along my hand, it got the linear velocity, so it has a higher probability of landing on its side. So different ways to throwing the dice leads to a different probability, and it's partly because of the linear velocity. And here is the second variable, the friction. In our explanation, you can know that the variation of angular momentum is affected by the friction. So we did an experiment that we toss the cylinder on different surfaces, that tar, whiteboard, and smooth stone, and the friction of tar is larger than whiteboard and larger than smooth stone. And here is the experiment result. There, blue dot is landing on tar, and gray is whiteboard, and orange one is landing on smooth stone. And as you can see, the larger friction has a larger probability of landing on its side. And here's the explanation that in Venn diagram, it's moving here on this direction, and friction is this, normal force is the blue vector, and spinning, so it has angular momentum this. And the variation of angular momentum can be described in this. F is the friction. So a larger friction also makes a greater variation of angular momentum, so it persists easily and until it stands up. So here are conclusions. Higher horizontal linear velocity may have a higher probability of landing on stack, and this is because there will be more time for friction to act on the time because the variation of the angular momentum is affected by time. And second, a larger friction may have a higher probability of landing on its stack, and this is because the variation of the angular momentum is affected by the friction as well. And final, a perfect three-side dice does not exist in reality because we can only find the variation of various cylindrical dice under a certain distribution of all the initial conditions. And so, which means that the previous experiment, the data is only applicable to my own situation. That if you toss a same cylinder, the result can be different with me because you and me, well, our distribution of all the initial conditions can be different, so the result can be different. It's all my presentation. Thank you.
Okay, thank you. Now is the time for opponent to ask short questions to the reporter.
First question, do you believe that when flipped from high enough, the three-sided dice is a chaotic system?
Can you repeat?
That you believe that if you flip the three-sided dice from high enough, that it is a chaotic system?
No. Yeah, it's chaotic.
Okay. Do you believe that three-sided dice is pseudo-random or random?
What?
Pseudo-random or random?
The initial conditions are random in a certain range and distribution.
Okay, so random.
Yeah.
Okay. Do you believe that a standard, how do you believe a standard cubical die should be rolled to ensure randomness?
What do you mean?
A cubical die, 6 faces.
The random on the initial condition, not the result.
So the rolling does not matter?
What?
So rolling a standard cubical die does not matter in this randomness.
Rolling?
A cubical dice, cube.
Yeah.
Okay. So in your theory, you use 2D motion in your simplified model. Why do you not do you think of using 3D motion and multiple and like a different axis of rotation that's not parallel to the surface would be a better way to express the motion of the three-sided dice?
We just did a simplified stacking model.
Okay. Have you considered coefficient of restitution, more bounces on the dice in your theory?
Yeah.
Okay. The following statement asks for a three-sided dice, so it's heads, tails, and sides, not faces and sides. Have you kept track of the heads and tails?
Okay, I think the time is up. So now is the time for to prepare for 3 minutes. Okay, it's about time. So, opponent, you have and up to 14 minutes. Okay, so please, the clock.
Okay, my name is...
Clock. Zero the counting. Okay, please start.
Okay. My name is Alex Dong, and I'll be opposing three guys from all-nighters. The opponent's ideal or structure of the investigation, we believe we should first investigate the phenomenon, then investigate the relevant parameters in the theory, and then the experiment and discussion, and find the ideal characteristics of the die. So first, we address the concept of the dice's fairness, identify relevant parameters, and then design and construct an experiment, and finally analyze results and idealize. So the pros and cons of the reporter's report was that they had a clear demonstration, and they considered a few factors such as ground prediction and provided good diagrams. However, they did not compare the theory and the experimentation in the experiment, only the simple model. They did not include error bars, so we did not know if they, so although they say they did it 2,000 times, we did not know the error in the actual data points. The probability theory, they attempted but did not explain it. They did not consider the surface unevenness, and they did not consider the physical composition of the die, such as like the material, the surface, the edge shifting, and the rigidity. They only considered like the geometric characteristics really, and they really didn't clarify the variables that well. On to the point of discussions. So first I want to discuss about the fairness of the die, the chaotic system, and it's like random versus pseudo-randomness, and also the assumptions, right? The equal head and tail landing probabilities. In their report, they only measured edge and face probabilities. However, the problem statement asks for their three-sided dice, which includes the heads, tails, and side. They also didn't mention anything about the size of the die, so only like the geometric ratio. So we believe that may be a factor. And they did not mention much about the physical characteristics. In the theory, they used like a 2D motion in their simplified model. However, we believe that we should use 3D motion to model the motion of the die. They also used one axis of rotation, which was parallel to the floor. However, the dice may be rolling with a different axis of rotation. And they did not consider the coefficient of restitution, how the die bounces multiple times in their theory. They considered friction, which we like to discuss, and they also did not consider air resistance, which we believe may be a factor. And in their experiment, the method of rolling dice seemed to be a bit imprecise. So we would like to discuss that, and like the surface evenness and material as well. They also did not discuss like dice interaction with possible external objects. For example, in the real world, a six-sided dice cube would be fair even if it interacted with other materials. So we would like to discuss if this also impacts three-sided dice. And also about the error bars. Like they had no error bars, so we do not know how precise the data actually is. And about the parameters, we can discuss the initial linear and angular velocity. But we also believe that they should also discuss initial drop height, which would be a factor, and the height to diameter ratio. We'd like to discuss that, how it would change with 3D motion model, and like they also did not discuss the dice material composition, which we would like to discuss. I'd like to go on to the discussion.
Okay, please start the discussion.
So you mentioned, you respond to my question that you believe that if the dice is rolled high enough, it is a chaotic system. What are the conditions for a chaotic system? Chaotic system where like initial change to the like a small change to the initial conditions lead to a totally different result.
Yeah, of course.
Okay, so what do you believe are other conditions to that? Or do you not have any? Other conditions for chaotic motion of the dice.
do you mean?
Okay, like, because you said the answer to my question, like, it was chaotic. You don't have any...
So we have the distribution of all the initial conditions. Then random, and every time you toss the data, you randomly select the set of all the initial conditions in the distribution. So you say that's a chaotic system?
Well, chaotic system means that it's sensitive to the initial conditions. So the opponent believes that that has to be a factor. Also, like the non-linearity of it, and you have to discuss the degrees of freedom of the system as well.
Does that equal to chaotic system?
Well, we disagree. On the random and pseudo-randomness, you said it was random. Why do you believe it's random instead of pseudo-random?
Pseudo-random isn't a real random because it's affected by a computer, but our simulation for the simulation.
Right. If not, then because for example, if you roll the dice from extremely low, then you might always land with one result. You have a graph. So if you have a graph of the initial drop height and the probability of, like, for example, landing on an edge, right? If you drop it at like extremely low, it might have like 0 probability. But if you drop it from high enough, it might actually have like chaoticness may also result into it like converging, but like in between it may like have some fluctuation. So did you ensure that you dropped your dice from high enough?
You think release height doesn't affect it?
Yes, we believe that you have to drop it high enough in order to ensure that you have correct randomness.
What should be high enough?
Well, you add consider like the base case of the chaotic system. You have to use like the condition of the chaotic system in order to. Because from high enough, there are certain.
What's high enough? What is high enough?
High enough. Well, I have to satisfy the conditions for chaos at high enough. As I mentioned before, conditions for chaos.
I don't think you don't really know what's chaotic system.
So the chaotic system, it has to be sensitive to the initial conditions, has that non-linearity and degrees of its freedom has to be fair and applied. It has to satisfy that it is sensitive to initial conditions. Did you make sure that that definitively satisfied that factor?
Why do you control? Why do you control the drop release height?
Because at high enough it will be random. But if it's not high enough.
Why drop the high position well?
Well, it's pretty intuitive. If you drop it from low, then if you drop it the same way from lower, then it would just end the same way.
That's because the angular velocity and linear velocity are small.
Okay, right, we're moving on. In your theory, you use like the simplified model, right? You had the dice, you were saying you had some medium velocity like that, right?
You saying the static model?
Yes.
No, that's randomly contact the table at first.
Your angular velocity isn't like rotating like this.
Yeah. In the static model, it doesn't have an initial angular velocity. It just yeah. This is the initial condition. Just the release height is equal to D. The reason that it rotates to whether that is because of the gravity force.
So you believe from that, like the way it lands, it depends on angular velocity. Like the probability density function of that will be the same as if you had initial angular velocity like that.
Is that model?
Yes, your static model, that's what it's saying, right? You have an initial angular velocity like that. This would be sort of how it lands, the probably density function of that. Okay, the opponent believes that you should use stir radians, like instead of like rotating it that way. For example, that way.
Are you focused on the static model?
Yes,
the static model doesn't consider all your probabilities.
But you do not have a model to take that data, right?
Can you use the microphone?
Oh,
We can barely hear you.
Okay, moving on. You did not consider anything about the physical characteristics of the dice. For example, its mass distribution. Do you think that would be a factor? Like the mass distribution?
Of course, but you are considered saying that it's a uniform mass distribution.
But the problem statement does not say that.
But that's very
trivial statement has very trivial. The problem statement also has physical characteristics.
Yeah, of course, but mass distribution is very trivial.
Okay, but it would affect the moment of inertia. If you have a different mass distribution, you might have a greater or less moment.
Yeah, of course.
So but that might affect the way probability of it landing in a certain way.
Of course.
Okay. So you do not consider them.
Yeah.
Okay. How about the dice material? Did you vary the dice material at all?
It's a 3D printer.
Okay, but if you were to use a different material, do you think the probability of landing on would be different?
Of course, because there's a deformation in reality.
Okay. All right. But you said that there exists no fair three-sided dice.
Yeah.
What if you know your exact surface, you know like everything about it, and you know the material of your dice?
But you didn't know the probability. You know all the initial conditions exactly, and still know the probability because the probability is always equal to 1 or 0.
Okay, but I'm saying if you like, I'm not saying that if you could find a fair three-sided dice for all surfaces, but just for one surface, could you do that?
Refresh.
Since you said there's no fair three-sided dice because of different surfaces, right?
Surfaces.
Yeah. If you the fair three-sided
This
dice.
is only one of all the variables. Just the context different. Not all the conditions.
I am saying if you know your surface, could you be able to find a fair three-sided dice?
Initial condition will be different. You ask me to find a fair three-sided dice?
Yes, for just one surface, not for all surfaces.
No. The distribution and range of all the initial conditions are different. So you just focus on the context difference and you ignore all the angular velocity, linear velocity, release height, and the orientation of the thing. And you just focus on the context difference.
The opponent believes that there should be a fair three-sided dice for one surface, or like each surface there should be a fair three-sided dice. Like model about your data, right? You do not have any data points. How do you know the error at all?
This is just a probability. So where should the error bar?
Can you move to the slide with your data? Like what would the error bars be for this? Like it could be extremely large, it could be extremely small.
It's very small because each point is 2,000 volts.
Okay, I think time is up. Opponent, please spend 1 minute for question.
So in conclusion, we discussed the conditions for chaos, the initial conditions, this sensitivity to that, and the freedom, which the reporter did not mention. We also discussed the randomness and pseudo-randomness of the dice, which is important because that contributes like the height of the dice it should be drawn at. And we also discussed the angular velocity of the dice, that it may not always be with one axis of rotation that is parallel to the surface. And we discussed the dice composition, which the reporter did not talk about, although the problem statement asks for the physical characteristics of a three-sided dice, along with the dice material. And we also discussed the initiation conditions and the error bars from the trials, which the reporter did not mention, and the opponent believes are extremely important to determine how well the models fit with data. Thank you.
Okay, thank you. Reporter, please stay on the stage. Microphone ready, okay? And also opponent. To the question of the reviewer to reporter and opponent and answers to the question. So please start. You have 3 minutes, wait a minute, clock. Yeah, thank you. Please start.
So what is the key factor of a random situation? Question for the reporter. What is the key factor of a random situation?
It's just random. You act.
Okay, thank you. And can you make sure that the possibility to land on face and tail is the same, and also for reporter?
Yeah, of course. This is the metric.
Okay, thank you. And for both of you, what is the most important geometrical characteristic for a fair three-sided dice?
The geometrical, which is the aspect ratio, is affected by the physical condition.
Okay, thank you. And for your opponent?
The opponent believes it's the height to diameter ratio.
Okay, thank you. And for the reporter, when you change friction coefficient, does the coefficient of restitution change?
Yeah.
And so do you think that will affect the result?
Of course.
Do you agree?
Yes.
Okay, so can you, how do you predict the direction of friction in your experiment?
I can't.
You cannot predict. Okay, thank you. And what is the main factor that determines the landing side of the dice? And for both of you, is it the motion in the air or the last collision with the surface? What is the main factor that determines the landing side of the dice? Is it the main motion in the air or the last collision with the surface?
Of course, the landing is the movement in the air.
Okay, thank you.
That's determined in when you predict it.
Okay, thank you. And after the dice collide on a table, you can simplify the situation into a stock and slide situation. And can you predict what will happen?
What? Different.
Okay, never mind. Do you think there is a certain height that might cause the dice not to be able to spin after it collides on the surface? And for both of you.
Cause it to spin when it lands on the surface.
After it bounces up again, and it will not be able to rotate in the air. Do you think there will be a certain height? Okay. Okay, thank you. And do you think that the rebounding height will affect the random situation? And for both of you, reporter first.
Yes, because the release height is
Okay, thank you. And for the opponent. Okay, so when the centroid of the dice is on the left of the normal line drawn from the contact point, can you predict which side it will land on?
This can predict by all the initial condition.
Okay, thank you. And for the opponent?
Sorry, what line?
Normal line. It is.
Yes,
Okay, thank you. And is there any possibility that when the dice is not
Sorry, time is up. Your question is not finished, so up here. The following will be the preparation time for 2 minutes. Okay, so now following will be the time for reviewer to take the stage. You have
Honorable juries and fellow competitors, I'm the reviewer from Team Excelsior, and the problem I'm going to review is problem of three-sided dice. And this of a rare occurrence. What should be the physical and geometrical characteristic of a cylindrical dice so that it has the same probability to land on its side and one of its faces? And the reviewer mainly focused on what is the characteristic of a fair three-sided dice, and what happens between the collision of the dice and the table. And this is where the reporter the torque of the dice, but they did not consider the energy transformation of the dice. And the reviewer believes that this is very important because only when you consider this, you can explain what makes the dice stop bouncing. And they have the lack of analysis of the collision. The reviewer believes that because it affects what the dice will land on at last. And they have provided a large sample of random saturation and know the real problem. But they did not analyze the rotation of the dice in the air, which the reviewer also thinks it land on at last. And they have failed to demonstrate how the final collision angle affects the result, which the reviewer believes that the main factor for the that affects which side the dice will land on. And for the opponents, first they have pointed is very important because it can affect the rebounds of the dice, and they have pointed out that they only but not the face and tail. And they have pointed out that they should have discussed affects the probability is what the reviewer believes is the collision, and they have discussion on important factors, for example, the mass of the dice, because the reviewer believes that the mass affects the rotational motion of the dice in the air. And they should have discussed the energy transformation of the dice, which has what I have mentioned in the reporter's pros and cons. And this is their first discussion about the random situation, and the reviewer believes that they should not quantify the way to throw the dice, because according to what the problem statement has asked, the problem statement has asked for a really random situation. And for the discussion on the initial height, the an unclear answer, but the reviewer believes that the initial height will affect whether the dice is random or not. And so the reviewer believes that they should consider the initial height also. And last is their discussion about the rotational motion. And the reviewer believes that the rotation motion of the air in the air is very important because while the dice does not rotate in the air, the initial condition will be the main factor to decide which side the dice will land on. And these are the points that they have missed. First is they have missed the motion of the dice in the air. As I mentioned, the rotational motion is very important. And they have affects the motion of the dice in the air. And they have discussion on the collision between the dice and the table, including these three kinds of conditions and the relative position of these two. And they have lack of consideration of the boundary conditions, things that it can affect the rebounding. And thank you.
Okay, following will be the concluding remarks of the reporter for 2 minutes, please.
This is the concluding report. Readiness is uncertainty of all the initial conditions. And next, if the distribution of all the initial conditions cannot be defined, that we cannot calculate the probability. So for the infinity amount of all the distribution of the initial conditions, so there isn't a fair three-sided dice. And the height is a variable. So controlling the influence the probability. And because a fair society does not exist, so the mass distribution and the coefficient of the restitution that don't matter. And finally, we can predict the exact motion of the dice if the initial conditions are known, but we cannot predict the motion if we don't know all the initial condition exactly. And I think the opponent and reviewer don't know the reason why it's fair to say that cannot be defeated. It's all my concluding remarks. Thank you.
Okay, thank you. So I would like to ask all three presenters to stay on the stage. Reporter, please. To the center of the stage, okay? So now we jury, please. Any questions? Yeah, please. The microphone needs certain time to align for the frequency. So if you prepare to ask questions, please turn on the microphone for frequency.
Okay. Yeah, maybe I can raise one question. Yeah, so I think apparently there's
microphone.
To the conclusion, yeah, because from order you say there's no perfect precise die, right? Yeah. And then but from the reviewer you say there should be a fair precise die. Okay, but maybe I want to raise something. When you guys try to think about symmetry point of view, the symmetry of the object. I think the opponent brings up a very good question about theory of operation. How does it apply to the cubic die? Right? Because I think somehow the symmetry is also maybe important. So maybe you could think on the symmetry of the die and how this precise die can work. Can it really be fair from the symmetry point of view?
From the symmetry point of view, the three-sided dice can be fair or not.
No.
So your answer is no. Okay. So question? On the others answer?
Well, symmetry, only the top, like the two faces, those are symmetric. Like only those two theoretically, if the system is chaotic enough, they would have the same probabilities or not the edge.
Yes, because we believe that when you combine the physical and geometrical situation, you can find the best situation for your dice to be fair. Thank you.
So, please. What's the most important factor? So answer from who? Which one? Answer from.
Only you ask about the most important factor.
Yeah.
And all the factor or variable are important.
Okay. I think that's enough. So any question from any answer from others?
Well, the geometric characteristic that just has to be the height to diameter ratio, and the physical characteristics would have to be the floor, the coefficient of restitution, and the friction coefficient.
Okay, I agree with the opponent because the ratio of the dice is the most important geometrical, but you have to combine it with also the physical characteristic, for example, the coefficient of restitution, so that to combine it will be the real perfect three-sided dice.
Okay, any other? Okay, please.
For the report you mentioned about the questions and the rebounding dice. So in your report, you just you don't think about the rebouncing of the dice.
No, I have considered it, but it's just a joke.
Okay, I just have a question. Do you think the rebouncing number will change the final probability? Maybe also for the other two.
Yeah, of course.
Why?
Because if he doesn't rebound, then it's just like a static model I previously shown. If the torque of the gravity will directly determine the result of the dice, then if there's the rebounding, then it can rebound and just like you taught it the second time.
Yeah, if it rebounds, the probabilities of the ideal dice should probably be changed for it to be fair.
When the rebounding height is high enough, the dice will be able to rotate after it collides on the table. So the reviewer believes that the rebounding height have to be high enough for the dice to be random. Yes, this is the question. Thank you.
Okay, I think the question time is almost up, so we move on to score. Do you want to ask questions? A short one, okay?
Very short one. I just follow the rebouncing problems. Okay, all the rebounds will happen most likely on the edge, right? Am I right? When the dice from the ground or on the table, the dice will rebounce sometime, right? Most of the time it should be correlated with the edge of the dice. Am I right?
Acceleration.
Dice bounce on the table, most likely it will bounce the edge. So how about the edge effect on the firmness of the dice?
The edge is now the 90 degrees, then the probability will change.
I think if the edge is like not sharp, as he's saying, it would form a microform, so then the probability might change.
I also believe with the opponent because when the edge is not 90 degrees, it may affect the side involved also.
Okay, so we move on to the scoring part. All you three can go back to the seat. Okay, all jurors, please raise your score for the reporter. I will read from my right hand side. It's 6, 6, 5, 6, 6, 6, 7, 6, 5, 8, and 8. And now please raise your score for the opponent. 8, 8, 7, 7, 7, 6, 8, and 8. And last, be the score for the reviewer, please. There are 8, 7, 7, 8, 8, 7, 8, 8, 7, 7, 7, and 8. I think we need certain comments. We got 2, for the reporter, we have 2, 5, and 2, 8. So, any comments from the 5? Yeah, please. Okay. I think the reporter treated the dice rotated in the air. Not so simple. Okay. This is not in the usual course. I think but it's rather complicated. It's awful and distinct. And then goes just treat it as a single sentence rotation. That's what I Okay. So another 5 from.
So I would like to comment on my 5 to the reporter. So from the report, so there's one very big drawback that leads to a lower grade. That is, you have the model, but you have only the model. You didn't show any relation to your geometric vector that you consider. You only have the basically the torque equation, and then gave us some simulation results. So we don't know how you get the results from your any conditions. So that is one. And the second point that leads to your lower grade from me is that during discussion, so I didn't see that you really participate in discussion. So even some answer, and you should try to discuss. You cannot just say this is not a question. So that is not a good way for discussion. So that leads to reply.
Okay. Then we have to 8. So, any comments from the 8? Yeah, please.
This report is just presenting what they found in the observation, even though the deviation from the theory is dramatic. I think they also try to discuss the difference between theory and experiment. So I think this is very good. Right on the answer. Even though the frictions is really not the only mechanism. So that's the reason why I bring up the symmetry issue. Symmetry of the die probably also play an important role. This is something
Okay. Then for the opponent, we have 3, 6, 4, 7, and 4, 8. The score is quite even, so any quick comments? Not really obligation, but any quick comments? I can give some comments. I think the opponent really tried to dig out some problem, but I think sometimes maybe the question you ask is a little bit not very straightforward to the heart of the question. So the reporter need to spend some time to catch up your problem. What's the real question and which part you can really answer. I think that's the really problem that during your discussion. But already pretty effective. All right. Then we got even more even score for the reviewer. We have 5, 8, and the rest to be 7. So any comments? Okay. So I think that the reviewer really prepared a very good template. And so your review become pretty very good, very effective. Okay. but apparently you are pretty nervous. But I think that's okay. So now I would like to announce a 10 minutes break. So please come back in 10 minutes. And meanwhile, I would like to ask all three teams to change your seat.
Why is that so?
那我们要不要签？签好的就好。
Yeah. Want to drink? 2, 3.
Hello. One, two, three,
Okay, I think it's time to